talked about if you have atoms, and you can have energy states associated with atoms, and if I have a transition from one energy state to another, the photon that's absorbed or the photon that's emitted has to have an energy that's equal to the difference between the two states, okay? But if you have a bunch of atoms together, they make a molecule, you end up having like multiple possible energy levels for the electrons. And they form in bands. And this is the stuff of chapter 29. So I get a whole bunch of electrons here, and they form these like possible bands. But when you fill up the bands, you know this. You can only have one electron in each quantum state, right? And so you like put an electron here, and then the next one, and the next one, and the next one. You kind of fill this one up. And typically, you totally fill this one up. Then you have a whole bunch of possible states up here. They're stacked on top of each other. And these are unfilled. So typically you have a bunch of filled bands, then you have some unfilled bands. So you have like a valence band and an excited band. There's various words that you can use for this. Okay, now, if you excite this system with a photon, here's the way it could happen. Hit it with a photon, knock an electron from the bottom of this band up to this band. But it could go from the bottom all the way up to the middle, or further up, or all the way to the top. Now, when they get into this band, you can have certain systems that work like this. The electrons can't just immediately kind of like jump down to where they came from. There's a little bit of a delay involved. It's like hard for them to make that transition. And they're up in here, and it's like, okay, I'm up in this state. I would like to be in a lower energy state. They can like fall down to the lower edge of this top band. And they do that by giving up energy typically as thermal energy. There's a vibration which is involved. So they kind of like work their way down to the bottom of this band, then they're hanging out here, and then they drop from this level down to this level or this level. And so they're dropping from the lower edge of this band down to here. Now, think about the energies. Think about the energies here, okay? How much energy did it take to make this happen? Then how much energy do you get back when this happens? Which is greater, the energy of the incoming photons or the energy of the emitted photons? Incoming photons have higher energies. So which has a longer wavelength? The incoming photons or the emitted photons? The emitted photons will have a longer wavelength because they're making a smaller energy jump. And so you can end up with materials that absorb and emit light in different parts of the spectrum. And this is the phenomenon of fluorescence. So I have this. Absorption, I got a whole band here, a range of possible energies because I can have a range of possible transitions. And this, the peak of it, shy of 400 nanometers. What part of the spectrum is this? Not visible, ultraviolet. Then when it's emitted, I'm having a drop over here. I get an emission band. The emission band over here peaked at 500. That's in the green. That's in the visible light spectrum. So you can have things that absorb light that you can't see and emit light that you can see. Okay? And that's the principle of fluorescence. Here's the thing. A lot of cleaning compounds are made with fluorescent substances. Why? Because it's cool and it makes things shinier. This is Mr. Clean. Oh yeah. And Mr. Clean, I mean, it's part of his name. Come on. He's under some pressure to really get things shiny. Oh, and look, how much shinier can you be than actually absorb parts of the spectrum that people can't see and re-emit it as visible light? There's ultra dawn. And here's a whole bunch of spectrum of cleaning products here. And cleaning products very frequently have fluorescent dyes in them. And why? Because it makes things shiny, seriously. And if you want just things to look bright and shiny, you emit the part of the spectrum that people are most sensitive to. You emit greens. And so a lot of cleaning compounds have green fluorescent dyes in them. Now it turns out there's other organic compounds that fluoresce really brightly. It turns out urine fluoresces really brightly. And which is here, and tonic water fluoresces really brightly too, which is over here, okay? And then, you know, you got kind of a glow off this. Here's a story of my use of physics in support of social justice. True story. There was a landlord in Fort Collins who got himself a black light and would go around to people's apartments when they moved out and say, I'm taking around a black light and I spotted a glowing spot on the floor. Oh, that means you had a dog or a cat who peed on the floor, and I'm spotting the urine spot and the fluorescent urine spot that they left behind. And so like a tenant advocate came and got in touch with me and said, are there things that you could use on your carpet which would leave a glowing spot behind? And I said, heck yes. I mean, like anything you use to clean these days has like fluorescent dyes in it. And so we made this like patch of white carpet that had this like, it looked stained and soiled and all kinds of awful things had happened to it by using like different cleaning products. And mostly what you sense if you use a black light is you're sensing the cleaning products. That was actually able to like get some of the keeping people's damage deposits overturned by proving that like the black light couldn't be, showing you that the people were keeping like unwanted pets, which is really, really fantastic. Anyway, that was kind of a happy thing.